So, welcome back to our video lectures on projective geometry. We are still dealing with conics, and this time we will deal with the nitty-gritty details of doing geometric primitive operations on conics. So what do I mean by geometric primitive operations? Things like intersecting two conics, intersecting a conic with a line, and I will give you a list of cooking recipes if you ever want to implement a geometry system that can properly deal with conics. Then you will more or less need the operations that I will present you in this video slot. So what I want to show you are operations like symmetrization of a matrix. So assume you have a matrix that should represent a conic, but it's not already symmetric. How do you make it symmetric? Well, actually, this is the easiest of our tasks so far, and we already had it. You simply have to replace your matrix by the sum of the matrix with its own transpose. This will give you exactly the same conic. Now come the really hard things. So one of them will be the opposite of this operation, the desymmetrization of a matrix. So assume you are given a conic and I ask you, what are the two lines in that conic if it is degenerate? So you have a conic and perhaps you know in advance it is degenerate, and the question is, how do you calculate two individual lines from that? So I give you a symmetric matrix A and you want to get two homogeneous coordinates of the lines consisting of this rank 2 matrix. This is one operation, and we will see this is a crucial sub-operations for the other operations I want to present you. The next operation we will deal with is the intersection of a line and a conic. So I give you a conic and a line, and I ask you, where are the 2 points of intersection? And even a little bit more complicated, I give you 2 conics, and I ask you, where are the 4 points of intersection here? So first of all, a little disclaimer. It's clear that each of those operations here can be performed in a kind of naive way. So you can, in worst case, use a numerical solver for finding the points that you have here. But well, we're doing a geometry lecture here after all, and we want to see what is the geometry behind these kind of operations. So let's start with desymmetrization, and in a certain sense this will be the most complicated part of that lecture. So assume you have a matrix A and you know in advance it is a rank 2 matrix, so it will decompose into 2 lines. So how can you get those 2 lines from this matrix A? So this matrix A here usually is symmetric, and now you want to have a non-symmetric counterpart of that matrix that is rank 1, because when you have 2 lines like here in that example, you also know you can write your matrix, or you can write your conic section as the product of those 2 lines, and to get from one to the other you have to somehow correct your matrix A by a second matrix delta, which doesn't change the conic. So the second matrix A essentially makes the following. So you have some kind of correction summons tau and mu and lambda. And these correction summands don't change the conic, because if you consider the corresponding letters in the conic, they occur as sums in the quadratic equation. If you take the d and from one of the d's subtract tau and to the other of the d add tau, you won't change the conic. So what we are looking for is correction factors tau, mu and lambda, such that this matrix here becomes a rank 1 matrix. And if we have that, then we can simply consider our two lines L and G in which this conic decomposes, and we know that this matrix can be written as G times L transpose, and we simply have to pick a non-zero column and a non-zero row to read off the lines G and L. And actually, since we won't get a zero matrix, there's at least one non-zero element, and from that we can figure out what is a non-zero column and a non-zero row. So, how to make this matrix rank 1? Well, a matrix is rank 1 if all its 2 by 2 minors are of rank 1. So we can, for instance, focus on the first 2 by 2 minor given by this part of the matrix plus this part of the delta matrix, and we have to make that rank 1, which means that the determinant of this matrix will vanish. And well, this is this expression. If you look closely at it, you will find out that this gives a very nice condition for tau. What we get is that tau has to be equal plus or minus the square root of the negative of the determinant that we have in this little block in A. And by that we can get also mu and lambda in a completely similar way. So what we get is that mu is plus minus the determinant of this 2 by 2 minor, and lambda is plus minus the square root of minus the determinant of the last 2 by 2 minor. Are we done yet? No, we aren't, because we still have the problem that we have to choose whether it's either plus or minus. So a global change of signs wouldn't matter, because then we get simply a replacement of delta by minus delta, which would also get a rank 1 matrix. But if we decided on one of the signs here, the other signs are determined as well. So there are two ways to get to these other signs. One of them is checking the other minors that we have here. So for instance, if you look at this minor here, it will involve all the three letters that you have, and there's only one consistent choice where you can get all of the 1 by 1 minors to be of zero determinant. But there's also a different way of getting it, and this different way involves considering the point of intersection P over here. Because what you actually can prove is the following, that if you take the homogeneous coordinates of this point P here, then you get a multiple of lambda, tau and mu. Which is a little miracle. I won't prove it here. You can read up the proof in the Perspectives on Projective Geometry book, but I will use this fact here. I give you a hint where this comes from. It comes from the adjoint matrix, and use the adjoint matrix in a clever way, and you will have this relation here. But we can really use this relation to create these lambda, mu and taus more or less all at once, or if we have one, we get the rest of them. First of all, I have to tell you how you get this point P. Well, in our last video lecture, I already told you how to get this one point P. What you simply have to do, you have to take the adjoint of your matrix A. This will be a rank 1 matrix, and every non-zero row or column will be a suitable representant of your point P here. So you start with matrix A, calculate the adjoint, from that you get P, and now you have to determine this alpha here, and you simply can calculate that, and here is the cooking recipe for splitting the matrix. So I already told you, start with calculating the adjoint, read off point P, and now the alpha is simply the quotient of the first coordinate of P and your factor lambda you may have calculated here. And if you have that, you get lambda, mu, and tau in a consistent way by simply taking alpha times p. And now you have your matrix delta. So you can calculate A plus delta and then read off G and L by simply considering a non-zero row and a non-zero column of that matrix. So this was the cooking recipe for desymmetrization of a rank 2 matrix. Now we will use that to calculate the intersection of a line and a conic. So let's go to the point where we intersect a line and a conic. So what are we given? So we are given the coordinates of the conic, which is a matrix, and we are given the coordinates of a line, which are simply homogeneous coordinates. So assume that our line has homogeneous coordinates L1, L2, and L3. We now will do the following, I would call it a little trick. So we will consider the cross product of L with some vector G. And we know that this operation is a linear operation in G. So essentially it must be a matrix times G. And the question is, what is the corresponding matrix? And here is the matrix that you have to take to make this equation here coming true. Well, you see, it almost looks like one of our delta matrices that we had before, and we actually will use it as a kind of delta matrix later on. So why are we doing that? And now it really gets tricky. So you have a line here and 2 points on that line. Let's focus on this situation. A line and 2 points on that line. This looks like a degenerate dual conic. You have 2 points and a double line through it. And we may ask, what is the equation of that conic? And if we have the equation of that conic, we can simply split it and get the 2 points of intersection. So our next question is, what is the equation of this conic here? And so first observation, it is a dual degenerate conic, as it looks like, 2 points and a double line through them. And here is the equation. So this looks like a little miracle. It's take the matrix L, capital L, and calculate L transpose AL, and you will get the matrix of the dual conic here. So this will be the matrix B of the dual conic that we then have to split. So why is this the case? Well, it must behave like the dual conic, and we can prove that it behaves like the dual conic, which means that whenever we have a line that is on that conic, so we have a line, say M, so this here should be line M, then it has to have a very certain property. It has to go through one of those points. So what we're asking for is we're asking for the solution set of this equation here becoming 0, and we want to prove that this solution set has the property of passing either through one of those points of intersection or through the other one. So let's simply see what we got. So we have L times M here, and we have M transpose times L transpose here. So we can rewrite this as the cross products of M times L times A times M times L. And now these are points, and well, now we see that it really behaves like our conic, because how can this expression here become 0? It can only become 0 if this here considered as a point and this here considered as a point is on our conic, which means that our line M that we have here will really have to pass through our point here. And so this only becomes 0 if m passes through one of the 2 points. And this means, well, it exactly behaves like the dual conic. So if something looks like a duck and behaves like a duck, it must be a duck. And so this equation here behaves like our dual conic, so it must be the equation of our dual conic. So now we can put all that together and get a cooking recipe for calculating the two intersection of line and conic. So what do we have to do here? Step 1, calculate L transpose AL. This is the matrix of the dual conic. Now split this conic. And splitting this conic, you remember, involved such a delta matrix. But we already know the delta matrix in this situation. It's the matrix L itself. So what we actually have to find is a factor alpha such that L transpose AL minus alpha times lambda has rank 1. So the task is now to find such an alpha, but we already showed how to do that. Look at one of the 2 by 2 matrices to get the corresponding factor that you need. And then we can simply split the matrix and we can simply read off the solutions as a non-zero row and a non-zero column of the split matrix. So now we know how to calculate the intersection of line and conic. You could also try to calculate the intersection by solving a quadratic equation. But I promise you, the equations will become more complicated than what we did here. So much about intersecting a line and a conic. Let's now come to the more difficult operation of intersecting two conics. In a certain mathematical sense, this operation is really more difficult than the previous ones, because for the previous ones we only needed square roots to calculate the results, and for this here we will actually have to use third roots to calculate the final intersections of those points, which in turn means that this operation cannot be performed by ruler and compass, for instance, but that's a different topic. So assume you are given two conics, and let's assume they have matrices A and B, both of them symmetric. How do we get the 4 point of intersections? And the trick here goes by using these two matrices and considering all linear combinations of those two matrices, because we know something interesting about those linear combinations. Those linear combinations will all pass through these 4 points of intersections, because both A and B evaluate to 0 at this point of intersections. So the idea now is to say, well, we take these linear combinations and we are looking for particularly nice representatives of these matrices that are easy to intersect. And it turns out that among all those conics through the 4 points, there are 3 special ones. So there is a degenerate conic connecting this pair of points and this pair of points. There is a degenerate conic connecting this pair of points and this pair of points, and there's a third degenerate conic connecting these 2 pairs of points. So when we sweep through the space of all conics through the 4 points, there are 3 degenerate solutions among them. So let's try to find one of those degenerate solutions, and we can do that easily by checking whether the determinant of our linear combination turns out to be 0, because when we have a full rank matrix, which corresponds to a non-degenerate conic, the determinant will not be 0, and if the determinant is 0, we will have a degenerate conic. So we must find a lambda such that this equation here turns out to be 0. And there are two remarks I should do at that point. First of all, I omitted our factor mu here because common multiples don't matter in our context, and without loss of generality, assuming that at least one of those matrices is itself non-degenerate, I can set mu to be 1. Second remark, if you look at this equation here, it turns out to be a cubic relation. So to solve that, you have to solve a polynomial where lambda occurs in the third power, and this is actually really harder than solving a quadratic equation, and it was a major breakthrough in the Renaissance period that people found out how to solve cubic equations. And as a matter of fact, you really need third roots to get to those solutions. But there are well-established ways to get at those solutions, and if you have that, this gives you kind of immediate cooking recipe of calculating the 4 points of intersections. So, step 1, find at least one solution of this equation. And if you found that solution and you plug in this lambda and you form the linear combination, you get one of the degenerate situations that also pass through all of our 4 points of intersections. So now you get one degenerate solution. You know that it is degenerate, so you can split it. So use our splitting procedure to make those two lines two individual lines that can be nicely intersected. And step 3, take those two lines and intersect them with one of the conics to get the 4 points of intersection. So we reduce the problem of intersecting two conics to the succession of finding the solution of a cubic equation, after that the splitting procedure, and after that the intersection procedure for a line and a conic that we already had. Let me make one final historical remark here. I told you that you need a cubic equation here, but if you do that naively, then it turns out if you want to intersect two cubics, cubics are quadratic equations. So intersecting two quadratic equations leads to a quartic equations. And actually what we did here is we found a way of reducing a quartic to a cubic equation, and actually it's easy to express a general quartic as the intersection of two conics. Actually you can use a circle and a parabola to make that, and by that you can really reduce the more complicated problem of solving a quartic to the simpler problem of solving a cubic. Okay, so far for the primitive operations. We worked through all our menu. In the book on perspectives of projective geometry, you find even more primitive operations. For instance, calculating the pair of conics that is at the same time passing through 4 points and being tangent to another line. This is a little bit more evolved. I really recommend to read that in the book. In our next video lectures, we will come to, again, a more theoretic topic. We will see how the border of a conic really resembles in a nice kind of wrapped up way the one-dimensional projective line, and from there we will go to the classification of interesting other types of geometries. See you there.